So we're going to make a return to thermodynamics now and take a look at the second and third laws of thermodynamics. We've already done the first law, which is the energy content of the universe stays constant, and that we represented with things like Hess's law and calorimetry. You might want to review those because what we do now is going to presume that you already have that knowledge. Okay, I'm going to start by taking a look at what we mean by spontaneity in chemistry, the spontaneous processes. Okay. The concept of spontaneous in chemistry, the word spontaneous, means that a reaction or process will occur without you doing anything to it. No outside intervention necessary. Thermodynamics tells us which direction a reaction will go in terms of spontaneity, but it doesn't say anything about the speed. If you want to talk about the speed of a reaction, you know we have to talk about kinetics. Thermodynamics really only looks at the initial and final states, state functions, not the pathway. The pathway is governed by kinetics. Okay, so if you want to put them together, thermodynamics and kinetics together, you get a much more complete picture of a chemical reaction or a process, if you want to understand it completely. So what makes a reaction spontaneous? What makes it happen without outside intervention? So this is a classic sort of reaction diagram where we have energy on the y-axis and reaction progress, which is this sort of vague nebulous term, which means like the path of the reaction. And you'll see that we start out with reactions at a certain energy, and then all of a sudden we go way up. You might remember that as being the activation energy of this reaction. And then we drop down, and in this particular example, the products are at a lower energy than the reactants. So if we wanted to find the enthalpy, or heat change for this reaction, all we have to do is look at the energy of the products minus the energy of the reactants, and we have delta H. Notice that deals with the outer 2/3 of this diagram. The inner third, the bit where the activation energy is and that very high spike on the graph, that's all dealt with in kinetics. That's your transition state, for example. Okay. We have a concept called entropy in thermodynamics. It's represented by the letter S, and it's a measure of chaos or randomness in a system. Okay. If a system is going to be spontaneous, if a process or reaction will be spontaneous, that means that we're going to increase the disorder, chaos, the randomness of that particular process. So as entropy increases, we become more and more spontaneous. And that basically goes towards the tendency of the universe. The tendency of the universe is for entropy or chaos or disorder to always be increasing. Okay? Another way of looking at entropy is, instead of just disorder, it gives us, it's helpful sometimes to look at what are the possible positions of a molecule. So if you have a solid, right, the particles of a solid are pretty fixed. Their position doesn't change. That's pretty low entropy. There's not a lot of possibilities for a solid particle to occupy multiple positions. It just has one position. It kind of vibrates there. You go to a liquid, and, well, then the particle can move it a little bit, and it can occupy several positions. That's more entropy. And a gas has an innumerable number more positions to occupy. So there's a lot of entropy in a gas. And if you think of it in terms of randomness or disorder, that makes sense, right? Solids are very ordered, liquids less ordered, gas is extremely chaotic. Okay, so that's the general idea behind entropy and how entropy works. So which has a higher positional entropy? S, remember, is entropy. Positional means the particles have more positions to occupy. So solid CO2 or gaseous CO2? Well, clearly that would be gaseous CO2, right? Because the particles have more places that they can exist. How about N2 gas at 1 atmosphere or N2 gas at 0.01 atmospheres? Same gas, same physical state, difference is pressure, right? So which of these two situations has more options for positions of the N2 molecules? Well, the lower pressure would be, right? Because at a lower pressure, we've got less gas particles, or we have more space, or any number of those factors, and that means there's more places for those particles to exist. Okay. Now, delta S is the change in entropy from products minus reactants, if you want to look at it in the classical sense, or from, how is entropy changing as you go from the beginning of a process to the end of a process. If the sign is positive, we're talking about an increase in chaos or disorder. And if the sign is negative, then we're talking about a decrease, okay? So if we add solid sugar to water, what's happening there? Well, the sugar particles, the molecules of sugar, are going from a solid situation to being dissolved, which means they're being spread out in the water. They're becoming less organized. So we should have a positive value of delta S there, okay? The more volume, the more positions they can occupy, delta S is positive. How about iodine vapor condensing on a cold surface to form crystals? So the vapor, the iodine particles are in the gas phase, lots of positions. They condense into a crystal. A crystal is the most ordered type of matter that we know. The particles in a crystal are extremely ordered, very, very unchaotic. So that would be a negative value for delta S. Okay, so understanding the concept of entropy and which direction entropy is going in a process is important to understanding spontaneity. Now, how does this work with the second law of thermodynamics? Okay, well, the second law of thermodynamics says that in any spontaneous reaction or process, there's always an increase in entropy of the universe. So everything in the universe tends towards a greater disorder. That's the second law. Okay, that means the delta S, the change in entropy of the universe. Now, the universe contains everything. And since in chemistry we look at system and surroundings, then the entropy change of the universe must be the sum of the entropy changes of the system and the surroundings. Now, usually those are going to be opposites. If the system that you're looking at is becoming less ordered, then it's likely that the surroundings are becoming more ordered by contrast. Okay? So it is possible for a reaction system, a process that is becoming less chaotic, that is becoming more ordered, in other words, delta S is negative. It is possible for that to be a spontaneous process as long as the delta S for the surroundings is larger than that and positive. In other words, the ultimate determinant of spontaneity in terms of entropy is the entropy change of the universe. If the universe's entropy is becoming more positive, the change in entropy is becoming more positive, in other words, it's becoming more disordered, then the reaction or the process should be spontaneous. Okay? So that's essentially what we're talking about in the second law of thermodynamics. Now, if the entropy of the universe doesn't change in a situation, then that means we're at equilibrium. Because, if you've got your forward reaction maybe becoming more chaotic, but the reverse reaction would be the opposite of that. And the amount of entropy change from forward to reverse should be exactly the same. So they cancel out. If delta S of the universe is less than 0, then we say that the process is spontaneous in reverse. Okay, we don't generally say it's a non-spontaneous process. We just say that the reverse process is spontaneous.